My hobby and line of work has allowed me to own and lay hands on some of my childhood dream equipment, and what I'll be showing you today is no exception. This is perhaps one of the pieces of car audio equipment that excites me the most, none other than the JBL Crown A6000GTI. Initially for sale in 2004 for $6,000, the engineers spared no expense designing and building this masterpiece. They were individually hand-built, and one amplifier would take over 8 hours to assemble. I'm going to be repairing this one for you today, which sadly has one channel in need of a service. So, to begin the disassembly, I'll remove the access panels. This one on the front hides the signal inputs and settings. The one on the rear is hiding the single very large power inputs, remote and subwoofer outputs. Here you can see the wiring configuration for bridge and parallel mono modes. Next, I'll remove the fascia and mounting bars. These bolts are very long and thick and take a while to unscrew. I'm doing this by hand for a better feel of torque and control. Always better to take your time with something like this. Removing a few screws through the mesh releases the perspex top plate. The rest of the bolts come out, followed by some smaller screws on the sides. Lastly, there are two large bolts on the underside that hold the silver mounting bars and black side panels in place. With those out, these pieces come away easily. Now all that's left is to remove the grille, which has screws all the way around. I carefully lifted the LED board and removed the connector which is fed through the grille. The last thing to disconnect is the lighting wires, which are connected to the main board on both sides. Once removed, the grille lifts away freely. Now we can get a proper look at this work of art on the inside. The power supply section not only looks beautiful, but this design is functional. The MOSFETs all have equal trace lengths to the transformer, as do the caps. There is perfect electrical symmetry throughout. There are 4 output inductors, meaning we have 4 separate amplifier circuits here. Everything here is assembled with great care, adhesive on every cap, well thought out header placement, heat sinking, current path flow. The transformer here is even heat sinked on the rear. Now we get our first visual sign of failure, a shattered MOSFET. This happens when the contents of the rail capacitors are dumped through the FETs in an instant due to a drive fault or shorting of the silicon inside. I've removed this header, which passes the smooth plus and minus rail voltages from the power supply to the amplifier board. This board is secured by screws on the underside of the case and some additional bolts through the board, one requiring the removal of this signal input assembly. The output board is now somewhat free, however the leads routing to the speaker terminals are soldered in. I do have enough room here though to complete a repair without further disassembly. Here you can see the output section cooling method. Fans blow air through these heatsink fins and over the circuitry underneath. The 4 inductors are screwed to raised mounts and also glued to the casing, which can be carefully pried off, making sure not to scratch the wire coating. The leads are clipped into rails on the main board and secured to the driver boards with glue. I levered the terminals off the rails, which also brings the driver boards out of their headers in one smooth motion. Now the entire output filter and drive circuit can be lifted out, giving us access to the output MOSFET clamps. It was here I spotted another MOSFET with visual damage. After removing the clamps, I was able to see which model MOSFETs are being used here. FQP17N40 tells us these are 17 amp N-channel 400 volt FETs. I also noticed a couple of different batches are used in parallel here. I'm sure they will have been matched for VT and RDS during assembly. I don't think this is the cause of fault here. I need to remove this and keep it safe, otherwise the thermal protection won't work properly. Looking under the output board, I spotted a stray strand of copper wire. These spell disaster if they get inside your amplifier, and is most likely the reason this failed. Just above this strand was some evidence of arcing on the underside of the board. Yeah, I reckon something touched here and shorted out. Alright, let's get to fixing this. First, I'll remove the whole bank of MOSFETs where some have failed. We can see some specs here from a survivor, ignore the RDS value. With the FETs out, I always check continuity on the semiconductor parts around the failed area, comparing readings to the other channel, which is still good. And yes, here I spotted a shorted Zener diode. The model is conveniently printed on the glass, 1N4735A. Next, I need to check the drive circuit along the gate path, so to find out which header pins connect to gate, I'll stick a lead in the header and check continuity. Gates are on pins 1, 3, 5 and 7. Final drive buffers are these J1Y transistors, and the driver itself is an IR2117S. To check the drive circuit, I'm measuring continuity from the pin through the 10 ohm gate resistor and then to the drive buffer. The drive exits the buffer on pin 3, however this one also shows continuity on pin 2, so this transistor is shorted. The next set along appears to have an open gate resistor. But the buffer transistor is not shorted. Set 3 has the same issue as set 1 with a shorted transistor, and set 4 appears fine so far. For good measure, I'm replacing all of the gate resistors and drive buffers for both channels. Since we're here, we might as well refresh these parts which have a limited lifespan. The driver chip also showed a short between pin 1 and 3, which is VCC and ground, so I'll be changing all of these as well. While fitting these, I noticed some more visually damaged resistors further up on the driver card, so I carefully tested every other resistor on these cards and changed any that were bad or out of tolerance. It was mostly the 5.1s here. After doing this, going through the board thoroughly and finding no other failed components, I was feeling pretty confident enough to fit all new MOSFETs and prepare the amp for a full power up, assuming it would be fixed at this point. I cleaned off the old thermal paste and added some fresh. And I reinstalled the heatsink blocks and MOSFET clamps. Next to go in was the output driver cards into their headers, followed by the output filter assembly. I reattached all the connectors and the LED status board, and I got ready for a power up. It was here that I noticed while probing the power supply FETs that it works in H-bridge. Half of the FETs have ground on the drain leg and the other half have 12 volts ready to be switched. The final thing preventing me from powering this up was the safety switch. There is a little magnetically activated switch here by the power terminals that only makes contact when the protective cover plate with the magnet on it is in place to prevent the user from electric shock. So, with everything in place, I powered it up and this happened. Those clips you've just seen were recorded over 3 years ago, and since then I've been working on this amp on and off without really any success until recently. But with 3 years more experience under my belt and a better idea of what kind of content you guys like to see, I thought rather than just making a repair video of this amplifier, I would talk you through the circuit step by step, each different section, what it's doing and how this amplifier works, how it runs. I've got the service manual now as well, which I didn't have at the time of recording those clips, and so what I thought we'd do first is talk through the service manual together, understand what it's saying about each section of the amplifier, and have a look at the schematic together as well, and talk about what parts might fail in a regular failure mode where output FET's short, what parts are most likely to get damaged, and just for pure interest for yourself, if you're interested in how this thing works, but also if you so happen to come across one of these for repair, you've got some solid information here that might help you get started on a repair. Okay, here she is. So let's go through this together and talk about the different sections. So this first part is really cool. This is the theory of operations. I absolutely love this service manual. It's great. This is just some straight up paragraphs about how the amplifier works. It talks you through the input stage. It then talks about how the signal goes through all of the preamplifier filters. It tells you the components on the board to look for specific functions of the preamplifier circuit. Talks about the filter. It also talks about how it goes through another filter to improve the low frequency response, whatever that is. Then talks about the error amplifier to decrease distortion on the outputs. Then we've got the modulator. This is where it starts getting interesting for Class D stuff. So basically we've got a couple of comparators here, which is going to be taking the audio signal is applied to the inverting input of both differential comparators. Then we have a triangle wave on there as well, and the sine wave is applied and compared to the triangle wave, which gives you your PWM output. So that's how we're converting the audio signal into pulses ready to drive MOSFETs in Class D. This tells you the frequency that the triangle wave should be, what pin and components it should be on. If you're missing the triangle wave, it then goes on to talk about how that's generated. There's a crystal oscillator here on the board that sets a bunch of different frequencies for various parts of the board. 125 kilohertz is the output switching frequency, but we've also got 250 kilohertz, which is divided down, and I think it also generates some of the frequencies for the power supply section and a few other bits and pieces. So yeah, if the crystal oscillator isn't doing its thing, then that's going to basically strip down any functions of this amplifier, I think. It then explains what happens to the pulse signals, the audio modulated pulse signals, 125 kilohertz. What it does after that, it goes into a voltage translator, which is on the output driver cards for each channel. Q301 and 310 is a voltage translator. That then goes into the MOSFET driver, the drive IC, which is U301 and 302 on the driver cards. And then we have a couple of buffer transistors after the MOSFET driver, which are likely to get taken out if the FETs die. And this bit's important. It says the FET driver output is referenced to VP14 and VP. So this is telling you the supply voltages and ground reference for the MOSFET driver. So that's important to know. We pause now for a qualitative description of the output stage operation. This is cool. This isn't necessarily super important when it comes to repairing the amplifier, but it will help you understand a bit more about how it works. This amplifier is very strange in the way that the output MOSFETs in the filter network are set up. The high side and low side MOSFETs don't see each other. The low side drain isn't directly connected to the high side source on the board via trace. It actually goes through some inductors, these great big filter inductors first. So you can actually completely isolate the low side from the high side by disconnecting the wires that lead to the inductor board from the bus bars on the main board. And that actually allows you to power the amplifier up, and regardless of whether there's a drive circuit fault or not, you're not going to kill any output MOSFETs, because the only reason output MOSFETs die is because the low side drain sees the high side at the wrong time, and the two potential voltages see each other and cancel out, causing huge dissipation of energy that's stored in the rail caps. But if you physically disconnect the high side FETs from the low side FETs so that they can't see each other electrically, then regardless of what your driver board is telling the FETs to do, turn on fully, turn off, turn on and off at weird times, they're not going to kill the FETs, because the FETs are just going to turn on and off, but there's no potential voltage that the FET can see opposing it to cause any damage. So it's a really, really cool way of designing it, and it improves repairability as well, allows you to repair it a little bit easier. So with no audio modulation, no input signal to this amplifier, obviously we have a 50% duty cycle there or thereabouts, because that's how Class D works. If it was more or less than 50% duty cycle in this setup, then we would have some DC offset on the speaker terminals. So 50% with no signal. It says the LP and LN inductors control the rate of rise of the current during this time, so that it does not act like a short during the couple of microseconds that they are on. So Crown have really designed this circuit with every detail in mind and every kind of form of reliability and perfection in mind. They've really optimized this circuit so that at no tiny fraction of a second there's any situation for the MOSFETs or the circuit that is undesirable, and everything is kind of really controlled and really dampened and really well designed. If you compare this to like a generic car audio amplifier, something coming out of Korea, or like the kind of Chinese copies of the Brazilian circuits, they are littered with literal design flaws. Like the MOSFETs on the output section cross-conduct horrendously. They run hot or idle. Even the power supply FETs might have the wrong switching frequency for the transformers used. All of these crazy issues that are just mind-blowing to any circuit design engineer that would actually exist on the market are actually present in a lot of these car amplifiers, because they're just not designed to be reliable. They're not designed with that kind of thing in mind. They're designed to be quick to produce, quick to design, low R&D costs, get them out the door. The customer's going to use it for a couple of years in his car, sell it on. If it blows, there's lots of other things to blame, and it's not like industry breaking. It's not going to cancel a whole gig if your amplifier fails, like this design is based on the Crown PA amplifiers, which need to be fucking reliable because they're powering like concerts and stuff that have millions of pounds put into them. So there's not that much overhead when it comes to car audio amplifiers and whether they are reliable or not. So they're not really designed with that level of detail in mind. Then we've got the output filter, which is the inductors made up of two individual filters. A signal passes through to field, blah, blah, blah. So yeah, we're just talking about the output filter. Then we've got the protection control circuitry. So there's quite a lot of protection modes in this amplifier. There's a few LEDs here on the board that we'll talk about in a bit. But we've got current monitor, current limiter, display circuitry, so that's telling you about the LEDs on the front and what the different LEDs mean. So this bit now talks about the power supply. So it says that we take 12 volts and convert it to plus minus 150 volt using full bridge topology. So yeah, this is a full bridge amplifier. The power supply section, okay, is actually not the same as what you normally find in car audio amplifiers. It's what does it say here? 6 parallel H bridges. So basically the power supply MOSFETs are kind of have like a high and low side, so you won't see a square wave on all of the power supply MOSFET drains like you would normally see in an average car audio amplifier power supply. In this instance, some of the power supply MOSFET drains have the square waves on them, and some of the power supply MOSFET sources have the square wave on them, kind of like high and low side on the output section. This bit's useful if you're troubleshooting power supply issues. It says when the remote signal goes high, the low voltage power supply enables. So there's a separate low voltage power supply in this board that activates first, and then the main 150 volts plus minus power supply enables. So we first of all get plus minus 24 volts. Once the voltage is at about plus minus 20, the large power supply is enabled. So that's interesting if you're troubleshooting power supply issues. The PWM chip for the large power supply has soft start circuitry to decrease the inrush current, etc. So that will just probably be gradually increasing the duty cycle of the pulses leading to these FETs, just kind of ramp up slowly. Tells you the peak to peak voltage of the square wave, and it tells you the switching frequency of the transformer, which is 1000 Hertz. It's normal for these amplifiers to emit an audible buzz, a bzzz sound when they are running. It sounds scary at first because you're not used to hearing that from a car amp, but because this transformer is switching at such low frequencies, it's well within the audible spectrum and you do hear it. I don't know for sure why Crown chose such a low switching frequency for the transformer as compared to 25,000 Hertz like you would see in most car audio amplifiers. The higher frequency you go in a transformer when you're switching it, the smaller it can be for the same power throughput. So by choosing 1000 Hertz, the transformer had to be absolutely huge in order to be able to pass 6,000 watts or more, you know, with headroom. So I don't know I don't understand the design choice of 1000 Hertz for this transformer, but I don't design switching power supplies. I don't know a huge amount about transformers, so I don't know what the benefits were of that and why they went for such a low frequency. We talk about the power supply protection circuit here as well, the low voltage power supply operation as well. So this is how it generates the 24 volts. And you see this 125 kilohertz, that is coming from the output board. That's the crystal oscillator, I think that it comes from. So yeah, that needs to be working for the power supply to even work. This is important if you're working on this amplifier. The power supply is designed to operate in continuous current mode, meaning that it always supplies current on both the plus and minus 24 volt rails. If the power supply is operated without the audio section connected through the ribbon cable, so that's the small ribbon cable that connects to the audio board. If you power the power supply board up without that ribbon cable connected to the output board, then you may very well damage some capacitors that it specifies here, because the voltage will rise up above where it's designed to, and it will rise up above the rating of those capacitors when that isn't loaded. So it needs to be plugged into the audio board at all times if you're powering it up, otherwise you can damage these caps from over voltage, so just bear that in mind. So now let's talk about how this amplifier works. We talk about maintenance. So where to begin? It talks about the fact that this uses surface mount stuff. This is cool actually, it tells you how to disassemble it safely without damaging anything, so have a read of that first. It tells you obviously the pin out of the main rail connector, which is kind of obvious, but just tells you about that anyway. Okay, so this is the output board. Tells you what all of these daughter boards and main boards are. So obviously we've got front end. These two boards are what take the audio signal and convert it into the modulated pulses ready for the drive circuit. So that's important. There's a lot going on this board, and some of these parts can fail in a drastic output section failure. You can get some damaged parts on these boards, which I'll talk about in a bit. We have the gate drive boards. So these are the driver cards. These are kind of the final drive for the MOSFETs. There will be parts on these boards damaged if you have dead MOSFETs most of the time, so that's important as well. We have the main coil PWA, which is the output filter inductors, the main filters. Not really going to get damaged, but you need to remove that before you can start working on the amplifier. Tells you what all the different cables connected are. I've got the current sense cable, power supply, got the main connector for the sort of preamplifier PWA input, so that's going to have the filters and stuff on it. And then on the underside of this board there is more output filters as well. So scrolling down a bit gives you the fault modes, the protection modes. So we've got the under voltage, over voltage, low voltage power supply. It tells you whether the low voltage power supply is any good or not on each rail. So it's really easy to see if there's a fault there. Power supply over current or audio section fault would be this one. So if there's no issue in the output section, it won't tell you what it is like it does with the power supply section, but it tells you that it's on the output side. So it goes into detail about those, which is cool. Oh no, I correct myself. It will tell you about the different fault modes on the output section. We've got over temperature, high frequency oscillations at output. I'm not sure what would cause that, but that's pretty interesting actually. That has that kind of protection mode. Loss of the plus minus 24 volts, loss of the rail voltages, DC on the output terminals, and too much current. See what this is about high frequency. The amplifier senses high frequency oscillations with frequencies outside the audio bandwidth. The most likely cause for this fault is that the diodes D801 and 901 on the output filter board are bad. If this does not correct the problem, replace the front end boards. So yeah, really cool solutions to issues that you might see. So now it goes on to tell you how to power this amplifier up on the bench, tells you what kind of current you'll need, tells you what kind of frequencies you should be injecting, and the setup for getting this up and running on the bench. Tells you there should be 12 amps worth of idle current draw. I think I got about 10 or 11-ish, so I mean lower is better, I guess. Now here's a really interesting one. Short circuit test. It literally tells you to inject 100 Hertz, short the outputs of the amplifier, and the signal light should flash every 3 seconds. So they're so confident in their short circuit protection that it's literally one of the things that it recommends testing. I mean, how many car audio brands would have this in the freaking service manual? None of them. This is important stuff to know once you've completed a repair. So it tells you how to calibrate DC offset on the speaker outputs, overlap correction, which is really important if you're replacing MOSFETs, drivers, or anything on the front end cards. That's really important to set, and we talk about that a little bit later in the live stream I did. You'll see a little clip where I was a bit confused about that and got it in the end. Talks here about ordering parts. I don't know if that's still going to be a thing. I doubt it, but okay, now we get on to the cool part, the schematics and the kind of board layouts. So here it gives you the locations of all of the components. We've got the power supply board here. It looks so cool, doesn't it? Even in drawing form here, the freaking power supply. The main amplifier board here, you can see where all the components are. Then we've got each individual daughter board card, all the filters as well, the inductor board, and then we have full schematics for this amplifier. So I'm not going to go through all the schematics because that would be really complicated, but I will show you where the main areas that you might want to be looking at if you're troubleshooting amplifier section faults, because that's what I had. Page 52 will give you a schematic overview of the output section, and it starts off giving you your plus minus 24 volts over here. We have simplified versions of the front end cards and the driver cards. So there are individual schematics for these cards that go into detail of all the components, but you can see here how we get the signal coming in to the front end card, kind of what it's doing, and then what pins each of these outputs are on. So we have the main outputs that lead from the front end card that has the modulated waveforms on it that lead to the drive circuit. We have VP drive and VN drive, and this stands for positive and negative. So that's basically going to be like high side and low side, with high side being VP, low side being VM. So we have a direct connection. There is direct traces from the front end cards PWM output to the MOSFET driver cards here. We have 29 and 30, 25 and 26 going into 1, 3 and 1 and 7 and 5 of these junctions. It also shows you where 500 kilohertz comes in from the crystal oscillator circuit over there, which then comes to a triangle wave. Then we've got a basic layout of the driver card, and we've got the pins where the signal comes in and tells you what it goes through, and then the gate outputs for each FET. You can see here we have individual pins for each of the MOSFET gates and also the source as well. This is just called current booster for each of these. Got the low side and high side. It calls both of them high side, and that's because the drive ICs that it uses are single output high side drive chips. But you can kind of think of this as high side as over here, which is VP, and low side over here, which is VN. So this is the one where you'll see the PWM on the drain. This is the one where you'll see the PWM on the source. We have this for both channels. If you scroll down a bit, this is literally a mirrored circuit. Then if we move along, after the MOSFETs, you've got all the output MOSFETs here. You can see it has the models of the output FETs that we slightly changed. Then we have some diodes here to the rails, which are important. You might want to check those. Then we have the filter stages here, and you can see here there are some test points that you can clamp your oscilloscope to. Now this bit's really important if you're repairing the output section, because it's possible that you'll have dead components in this area. If the MOSFETs fail, okay, naturally you'd expect them to take out stuff on the driver card, which we'll talk about in a bit, and maybe if we're really unlucky it will take out some of this stuff that connects to the driver card in the front end card. But on the main board, on the actual main circuit board, aside from the FETs, you're likely to kill these diodes. There is D315 and 316, and there's other ones for down here as well. There's I think in total 8 of these diodes. They're 6.3 volt Zeners, and you've got the model number there, and these will likely fail in an event where the output MOSFETs are shorted and have spiked back a bunch of crap throughout the circuit. This was the case in my repair here. I had some of these diodes that were faulty. Now what this circuit does is this circuit is responsible for generating the VP plus 14 and VCC plus 14. So this is basically the 14 volt supplies that the driver card uses to drive the gates. So obviously in order to turn the MOSFET on, the MOSFET needs some voltage above its source in order for the gate to turn on the gate. It's got VP plus 14, which is generating plus 14 volts above the low side drain essentially. It's actually connected to high side source, but that's what you'd normally expect to see in an amplifier that you may be more used to repairing. So the high side source, the wave that's on the source, which should be the same as the wave that's on the drain over here on the low side, it generates plus 14 volts above that. Similar to how your bootstrap circuit would work in a regular half bridge amplifier that uses a bootstrapped high side. You've got the bootstrap pump, which generates a supply voltage above the output PWM of the low side. So that's kind of what it's doing here. Just got this little circuit here that generates 14 volts above the output wave for the high side drive, and then the low side drive, we have a similar circuit down here, but it's generating 14 volts above a negative rail, but it's the same circuit that's responsible for doing that. So yeah, if you've got an output section failure, check these diodes and stuff for shorts. Make sure that these inductors here have continuity on them. Absolutely check, or maybe just straight up change these diodes anyway, because they do get hit when the output's short. Okay, and then we have the output filter board. Okay, so this is the schematic for the driver cards. Relatively simple looking. You'll see here we have the voltage coming in from the front end card, which is labeled here as SP plus and SP minus. Okay, and we have this going into what I think it called this voltage translator or something. It got a bunch of transistors here. I think it said maybe it's acting like a really low noise op amp or something, but yeah, bunch of transistors here, and these all have high value resistors, 10k to ground, so they should be fine. You shouldn't have to worry about these. I didn't have to replace these components, these were all fine. The components that are likely to get hit the most often in an amplifier output section failure are going to be, if we scoot along here, so we've got the gates and sources connected to MOSFETs here. So when they fail, they're going to take out gate resistors, which are these 10 ohm bad boys here. There's lots of 10 ohm gate resistors. We're going to take out these transistors, which we've got the markings for here, the model numbers. It's going to take out these 5.1 ohm resistors here as well. So check all of those, make sure that they are okay. There's another one there as well. So any low value resistors, there's another 200 ohm there. So all of these low value resistors that are basically connected and have a connection to the gates and sources of the FETs, these are likely to get damaged. So you're probably going to need to change these parts. If we go back further from the 5.1 ohm resistors, if you get a bit more unlucky, then you'll also kill the driver, which is an IR2117S. It's a single output high side driver. You can see here that we've got this VCC, which on this part is connected to the negative VCB. We've got a test point for it there, and the VB is connected to the positive voltage, the VP plus 14. So that's what was being generated over on the main board, like we explained earlier. Then we've got our input here from this kind of voltage translator, or this low noise op amp, whatever it is, over this side, coming into pin 2 through a couple of final little buffers down here. There's a 10 volt Zener as well that you might want to check is okay. So yeah, if you want to check this driver, you probably just want to use your multimeter and just make sure there's no low resistance or shorts between HO is the pin that's going to get hit, because that's the one that's connected to the kind of rest of the drive circuit. Also check VB, so check between HO and COM, or VB and COM, check between HO and VCC, etc. If you have a short between any of these ones and the in pin, then you might want to go back and check some of these other transistors as well, way back here, make sure they're not shorted. If you get super unlucky and a bunch of these transistors are failed and shorted or bad, then it might have taken out some parts in the front end card that connect to these inputs, which would be pretty bad. So now you've got a rough idea of this one. Let's go and have a look at the front end card, which I think is... okay, that's this one here. So let's take a look and see. This circuit over here is responsible for activating the Class D switching. There's a bunch of like logic gates here and stuff that will either allow output switching to begin or disallow it if different states are detected. So you've got current limit state there as high. You've got current limit here as well. You've got run and standby. There's a circuit down here that is responsible for setting a turn on delay. You can see here with this component down here, this op amp. You've got over temperature as well, and it tells you that it goes low. You've got timing cap, which will be responsible for like the turn on delay. So yeah, a bunch of circuitry over here if you're having issues where you can't get the Class D to activate and everything else seems fine. Check some bits and pieces over here. But in terms of the modulated PWM that makes its way onto the output driver cards, that is all over here. So you can see here we've got a 74ACT08D. So it tells you the pins on these that have the inputs and outputs that send the PWM to the driver cards. So yeah, if you get really unlucky, you might have to replace these components, U504, U507, etc. And same for the other card. That'd be the first one that I would replace, because that's going to be the next thing in line that's going to get taken out if there's big spikes coming back from the gate driver card. It tells you here as well that test point 504 should be high if the amplifier is in run mode, is activated. So if TP504 is low, then you know the amplifier is not allowing the output section to oscillate for some reason, and you can find out what reason that is by reading some test points down here to see what mode is detected, and also look at the LEDs. I imagine the LEDs will probably tell you as well. Yeah, and then further back from that, you've got a couple of LM361s as well. They might be damaged if the 74ACT08D is damaged, but really the damage has got to stop somewhere. So those are going to be the components that are most likely to fail. You've got a couple of 75 ohm resistors here as well that are in series with the modulated output. So yeah, check these, change the U504 and the U507, and if you still got issues on this front end card, change the LM361. But yeah, really the damage shouldn't really be going back too much further than that, you know, unless you get like super unlucky. But you can follow the schematic back. You don't necessarily need to understand exactly everything on the schematic and exactly what component is doing what and how it all works, but if you just need to kind of think, right, this part failed and it killed this part, so you can just follow your way back down the schematic and see what things are connected next along in the chain, and that's the next likely place that's going to be damaged. So then you've got an idea, oh, maybe I'll try changing this part next because that has connection to that. So yeah, that pretty much covers it for the schematic on the common things that will fail when you have an output section failure. So enough of the paperwork, let's show you the board in front of me, and I'll tell you exactly what parts failed on this and what we did to get it back up and running. And one of the things that was most important I haven't actually mentioned yet, because it's not something that really appears in the schematic. So here she is, and first things first, because we've removed this cover here, it won't actually power up unless you short out the safety switch. Just kind of stuck a little screw. That's something that I had laying around 3 years ago that I just shoved in there to make contact on those pins. So you need to bridge over the pins of the safety switch to allow this amp to come on without the cover in place, and that's to protect the end user from high voltage on the speaker terminals. Pretty cool. Main power supply transformer. I love the radial design of the MOSFETs on here. I think it's awesome. Over here we have the plus minus 24 volts power supply is going to be in this section here, and we also have some smaller transformers which is going to be probably plus minus 5 or a lower voltage. There's a resistor here. Don't be alarmed if this one gets really freaking hot. If the amplifier detects that there's a fault, which is a really clever thing that it can do actually, if it detects that there's overcurrent or some kind of problem, then when it turns off, it will immediately dump the rail voltage, the rail caps, into this resistor. So this resistor will reach temperatures of 150 degrees Celsius or more. Don't be alarmed. It's just a protection circuit doing its job. It gets rid of the high voltage rails to protect any further damage to any components, which I think is really clever. So that's something that I noticed I was a bit confused about at first. I was like, damn, this thing is getting freaking hot, but it wasn't a problem. It's part of the protection circuit. So yeah, this is all low voltage regulation stuff. We've got MOSFETs here, which will be running transformers. You've got a couple of linear rectifiers, a 7815, 7805 here. So yeah, it's generating lots of smaller voltages for all the control circuitry to work on, etc. There's your main rectifier, just one rectifier that then outputs to these wires, which go over to the output board. Now the ribbon cable that it was talking about earlier, not to disconnect and power the amplifier up, is this one. This ribbon cable here is transferring the plus minus 24 volts and a bunch of other stuff, and it's also transferring some protection signals back to the power supply board. Don't disconnect this one and power the power supply up, because you will damage some of the capacitors. I think it's these two from memory, because the voltage will soar up above their maximum rating. So keep that connected. Got these three ribbon cables here, which can be a bit confusing. One of them is for the LED board, and the other two are for the RCA input board, but these two are the exact same connector, so don't go plugging the wrong one in to the wrong thing. Don't go plugging the LED board one into the RCA board. It's actually labelled here on the board, which we can see if I get the torch on. The bottommost ribbon cable here is actually labelled display. So the bottom one will go into the LED board, which you probably won't be using too much. And these two top ones are the ones that go into the RCA board. So bear that in mind. So this board is our sort of preamp board, if you like. It's got lots of filters and stuff on there. Usually not going to have any issues with this. It's also got some protection circuit stuff on here. It's measuring the overcurrent on the output filter board. So you're probably not going to be working on this one too much, but there are schematics for that if you need to diagnose it. But these are kind of important. These two boards are the front end cards, and these convert the audio waves coming from the preamp board into pulses ready for the driver cards for the MOSFETs over here. So the components which I was talking about are important earlier that you might need to replace in event of a failure. There is these two chips down here, which are the ACT chips, which are the ones that actually feed the PWM to the driver cards. They're the last thing in the chain. So these ones might fail if you have really bad failure on the output driver cards. And then just above them, we have the LM361s, which are just before those. Now, these chips have their own supply voltage. They have their own power supplies. See these two little 8-pin chips just below them? These are voltage regulators that are dedicated to supplying voltage to these ACT chips. So if you're not getting power to these ACT chips, then look at these two voltage regulators here just below them, because they supply the voltage for them. Just in front of the front end cards, we have the potentiometers that you will use to set the overlap on the output FETs once you have completed a repair. So that's where they are. And you've also got some potentiometers on the front end cards for setting the DC offset on the speaker terminals. And I can't remember what the other ones do. Might be sensitivity, for example. But yeah, one of them is for the DC offset on each of the channels. So that's worth bearing in mind as well. Deep in here is the crystal oscillator Y40, which is responsible for generating the clock signal that the whole amplifier runs on. It is the source of the 125 kilohertz, but that's divided down. I can't remember what frequency this oscillates at, but it's very high. It gets divided down by a bunch of components, probably these ones in front of it. But yeah, a bunch of different parts in this amplifier use signals that are generated originally at that crystal oscillator. So that's where all that comes from. Then we've got a bunch of rail capacitors here, probably going to be fine. Now, if we take a look at the rest of the output section here, we've got the two driver cards, which are situated here. They're mirror images of each other, obviously. And the components that I was talking about that might fail on the main board, which are the diodes, which are feeding part of the 14-volt supply for the drive ICs, is these ones here. There's a bit of flux left on there, which I'll clean up. But there's the two Zener diodes, which are in series with each other. There's two there, two there, two there, and two there. Onto the actual output gate driver cards themselves, and I'll probably cut to a clip here where you can see it a bit better, because I don't want to keep taking these in and out because the headers are a bit dodgy, which I'll talk about in a bit. So you've got your final buffer transistors here with a 10 ohm gate resistor. Then you've got your drive IC, the 2117. Then you've got some 5.1 ohm resistors just above this section here. There's a few diodes as well, which you can check. Lots of test points on these cards. And these test points here, you can actually use, because if you check the schematic, they are actually connected to the input pin of the 2117. One of these test points is connected to the input pin, which is really useful. And then the other pins are connected to the outputs or before and after the drive buffers. So real nice, easy test points for you to stick your oscilloscope probe to save you from accidentally slipping and shorting something out from trying to probe the actual component leg. Really useful. So there's not, like I say, not really a huge amount going on these cards. Once you look at the schematic, it's pretty simple, and it's all kind of mirrored and very much of the same thing, just lots of it. So quite simple once you get to know it. Now, let's talk about these headers. These are actually a nightmare. These are the reason that I struggled with this amplifier so much, because I was looking for failed components and wasn't finding any. The issue actually was that these headers, the pins, weren't making a good contact against the forks in the headers. And it took me a long time to figure that out, because they felt like they were going in great. And it's very unusual that I've come across this issue. Headers usually just work. But yeah, They're not easy to replace either. These headers are surface mount headers. So the pins are actually, the kind of forks are connected to the main board in surface mount. They don't go through the PCB. So it's not like I can just very easily replace them. They have alternating pins going forward, back. I haven't really looked to see whether I could buy replacement ones of these, but replacing them would be quite tricky because there's lots of bus bars in the way and stuff like that to prevent you from easily soldering the pins. So if you're repairing one of these and you're removing the output drive cards, I would recommend taking some pliers like I did in the live stream and pulling the plastic headers off of the pins. Now a couple of the pins might come desoldered because the solder will, it'll pull them off the solder, but it's relatively easy to resolder just the odd couple of pins. But pull them off the pins, pull them off the forks and squeeze them closed a bit more, like squeeze them tight again. And then what I do once you've done that, after you put the plastic tops back on, is I would tin these legs. So these pins, these legs here on the driver cards, I would actually go ahead and apply some flux and apply some solder to them to thicken them up a little bit. By tinning them, they'll be a bit thicker and they'll be fresh because the metal might have oxidization on it where it's kind of old, these amplifiers now. So I would tin these legs to make them a bit thicker, make them a tighter squeeze in these headers, and just to make a nice fresh new contact metal to go against the forks in these headers. This was the biggest issue that I've had with this amplifier, which prevented it from working. It's why I've had it for 3 years, is I was looking for dead components, I was looking for issues on the main board. I've tried swapping around all these freaking diodes you can see, like I've tried swapping them around from channel to channel, trying to work out what was wrong with one of the channels. Turned out that it was just the headers were bad and not making a good connection. So I am skeptical of this going forward. I've done my best to make a solid connection in there, like I say, we're using the methods that I described. Ideally, I'd love to just hard solder these to the board, but they're not through hole. So it would be a lot of effort and some modifications to actually get these hard soldered to the board rather than in headers. Not something that I'm really too confident doing just now, but I've done my best to make a solid connection to the existing headers and the existing pins that are in there. So I'm praying that that is reliable going forward. Not ideal for a car amplifier that's going to be subjected to vibration, but we've got to work with what we've got here. And obviously you've got your output filter inductors and they're double stacked. There's two there. These are glued to the bottom here. So if you unscrew everything and you can't get it out, it is glued. Now obviously don't use a metal screwdriver to pry this up because you don't want to scratch off the laminate coating on these wires. So use something kind of plastic or non-scratching to get under there and pry and get the glue to break. And then this, literally just lifts off. You've got the wires here connecting to these headers. They're pretty self-explanatory. They can only go in one way. This is the wire that is sensing current on the output filter board. So if you're having issues where the amplifier has overcurrent issues, like it's going into protect from overcurrent, and that can happen if you have drive circuit issues, not necessarily because there's overcurrent. Even if you've got the MOSFETs removed, sometimes the amp will go into overcurrent protection. You can just go ahead and disconnect this, and that will allow the amplifier to power up without going into overcurrent protection if that's what's preventing you from performing further checks. So yeah, having this disconnected will allow the amplifier to power up and try and start activating the output section even with no MOSFETs fitted. Taking another quick look at the front end cards, if you're wanting to see what's going on with the components here on the front that we talked about earlier, obviously you don't want to get your probe in there. There are some really useful test points on the back of these cards. These top ones, these topmost test points, are the PWM before it enters the ACT chips. And these test points at the bottom are the outputs of the ACT chips. So when you first power the amplifier up, you'll get PWM, provided everything else is working, on these top test points here. And then when the Class D activation enables, and the output starts trying to switch, these bottom test points will have PWM on them. So yeah, if you're getting PWM on the top ones, but nothing on the bottom ones, then Class D switching is not being told to activate due to detecting a fault somewhere perhaps. But if you're not getting any waves, any PWM on the top test points, these top 3 test points, I think there's one more slightly up to the right as well. If you're not getting any PWM on these top test points here, when you first enable the power, because these ones run off of the 24 volt plus minus supply, so the actual rails don't even need to be there for this to show PWM, then it means that you've got an issue with the earlier circuitry, which is generating that kind of clock frequency or converting the audio into pulses. So that's important. You should always have PWM on these top 3 test points on both of these, and then you'll have PWM on the bottom 4 when Class D starts to activate. Now, without any MOSFETs fitted, if you have the MOSFETs out of the board and none of them fitted, then you will need, from memory, to inject a bit of audio signal into the amplifier. So you need to connect up the RCA board, inject, say, 40 Hertz, and then what will happen is you'll get a 40 Hertz square wave on these test points, which will make its way all the way to the output drive cards and also to the output MOSFETs. Now, because of the way that this works, it's not bootstrapping really the high side, and just because of the way the output drive circuit works, you are able to view a square wave, drive wave, PWM on the gates of the low sides and of the high side, which is unusual. Often you won't really see any PWM on the high side gates without MOSFETs fitted, because it's using the usually amplifiers with a bootstrapped high side will use the PWM output from the low side FETs to pump up and generate voltage for the high side supply. So you won't usually see any drive wave on the high side. But because this has a separate supply voltage for high side that doesn't use the low side drain to generate it, we actually see high side pulses on the gates as well as low side pulses. So yeah, you should have pulses on low side, high side, low side and high side without any MOSFETs fitted, but you will need to inject some audio signal from memory to get that to actually show up. That's a really good way of testing that. Both the main board and the daughter boards are littered with test points, and while the service manual might not go into detail about each of these test points individually, you can look at the schematics, and if you're following the schematics and you see, oh hey, I should check whether there's voltage at this point here or signal at this point here, there's usually going to be a test point at any kind of known useful area where there'll be like an input to a chip that has waves on it, or something that has a critical voltage on it, like parts of the protection circuit that go high or low at different times. So the test points are really, really useful and make it a bit safer to work on and just easier for you when you're diagnosing faults. So hopefully that's given you some better understanding of this circuit, how it works, and if you're attempting a repair, there's probably going to be some valuable information there to help you along the way. Now, after having this amplifier in the workshop for the best part of 3 years, and struggling to kind of find faults to begin with, putting it to one side for a long time, sort of getting it back out, having another look, not really getting anywhere with it, I did find the root causes for the faults, and as you kind of see in the first part of this video that I took many years ago, those were the main faults. There wasn't really much else wrong with it other than the stuff I found a long time ago, that being the MOSFETs, the gate drivers and the gate resistors, the 5.1 ohm resistors, the drive chips, the drive ICs, the 2117s were bad, and also the diodes, which are responsible for helping to generate the 14 volts above negative rail and above VP. So those were the bad components as a result of the failure. However, what I wasn't aware of was the issues with the headers, and that they were actually causing me to believe there was more circuit damage because I just wasn't getting any switching. I wasn't getting any pulses at all anywhere on either channel. So this is going to be a common kind of point or weakness point for these amplifiers, especially if they're being worked on and the cards are coming in and out and stuff like that. And these headers are just really, really bad and I don't like them. So it was in the live stream that I did, the final live stream I did on this amplifier, where we finally got some output MOSFETs fitted after I had made the drive waves make their way to the gates as intended by sorting out the headers, and yeah, it seems to work absolutely fine. So I'm just going to put it back together because it's currently all still in pieces. I'm going to reassemble the thing and give it a full test, give it a nice long test on the workbench, playing into a load, playing audio, and if I get time, I'd love to install it in my van, but I guess you'll see whether I do that or not at the end of this video. So first thing that needs to go back on are these heat sinks, and these, you'll be surprised to find out, don't actually have any electrical insulation between the back of the FETs and the heatsink block, and that is because each block is isolated, is separate from one another. So this block here attaches to the high side FETs of this channel, and the high side FETs only. So it doesn't need to have electrical isolation between the FETs and the heatsink block because it has common voltage on all 4 of these FETs. The little diodes in the middle are actually isolated by this ceramic pad in the middle here. So this block will be electrified with rail voltage in the same way that the low side block will be electrified with the rail-to-rail switching that the low side has on it, which is quite scary. Massive block of metal that is completely live. So yeah, we just need to mount these back on. So they go up in here. So quite a nice cooling solution. You've got these fans here which are blowing air through this kind of channels, these channels here underneath the board. The air will pass through these fins, taking away a lot of the heat, and the fact that there's no electrical insulation means that there's great thermal coupling between the FETs and this block, which is going to extract heat away from the FETs really quickly. So that's cool to see. So that's going to go on there. The air is then going to pass through the fins, and it's also going to be taken over the final filters, so these big resistors, which will probably get quite hot, and some of the other components on this final filter board. So yeah, some good airflow solutions in here. These just fix in place by clamping to the FETs. There's no screws into the metal through the plastic or anything like that, so just need to get some thermal paste on there and these MOSFET clamps, and it goes on like that. The FETs get clamped on like that. So I've been reassembling this in the living room just because it gives a bit more space. I really wanted to get this finished and get some demos of it for you guys in the van. However, it has a Perspex plate that goes in here. It has like a Perspex kind of front that slides in. It's still at my old house at the workshop, and my parents live there, so they've got that. I've confirmed they've still got it, so they're going to post it up to me. This video is already knocking an hour long. I felt like if I put the demos of me playing this, especially in the van, and like, you know, showing it all playing and stuff, it would kind of get lost at the end of this video. The majority of the viewers will have like gone at this point, just kind of how it goes with the YouTube watch thing. So I want to make a separate video of this playing, and yeah, we're going to connect it up in the van, I think, provided I can actually get the top plate, the Perspex plate in, and get some tests in the van before my customer wants to come and collect it, because he's quite keen to come and get this now, as you can imagine. So yeah, he's happy for me to do that, and it will also be a really good test for it as well, to make sure it's all solid. But it'll be cool to compare it to the Triumph's HD10K that I've got in there. My theory has always been that once you get beyond a certain kind of like power range with car audio, the difference in how a system's going to sound is solely defined by power. The more dynamic headroom and power you have on tap, the better the thing is going to sound, regardless of like the intricate designs of the circuitry and the THD and stuff like that. What we have here is probably the pinnacle of high power, high quality bass amplifiers. You don't get much better than this. What we have in the van at the moment, the Triumph's HD10K, is subjectively one of the lowest quality high power amplifiers that you could get in terms of THD and stuff like that. So it'll be really interesting to actually, for myself, to sit and listen to these two amplifiers back to back and be like, well, what sounds better, having more power or having a better circuit design? So hopefully I'll be able to do that. So that's going to be in a next video coming once we get the top plate, Perspex in on this, and the few bolts put in it, and yeah, get it tested on some bass for you guys. But hopefully this video has been insightful, and I hope you've learnt a bit about this amplifier. Obviously I could go into so much more detail about the inner workings of this, but this video is already an hour long, and I'm sure that there was enough there to kind of whet your appetite. If you really want to know more, then the link to the service manual that I used in this video is in the description. So if you are keen to look at the service manual and study the schematics and fully understand how this thing works, then you can take a look at the schematic with the link in the description, so I'll post that in there. But yeah, stay subscribed to find out more videos on this and other stuff that I've got coming soon. Thanks for watching, guys. See you in the next one.